Dear student, now we'll see the instructions call and written. With this, I can relate the function in C programming. How we can call the function? Like we call it as here the subroutine. Subroutine, it means that it is a subprogram written outside the main program. It is a sub part of the program. We can call the program so many times. So it reduces the length of the program and reduces the total memory size required for the whole program, and easy to understand the program what we wrote. As well, it is clearly mentioned that the subroutine has a part of a program. So in assembly program we can call the subroutine, like how we can our program counter as jumps to a particular location and executed that instruction. Here only the difference is that main thing is once you call, that is the program counter has fetched that call instruction, the specified location, it should be a near address, that is what we call it as a call, that holds 11-bit of an address. For example, I call a call next. This address, it is in 11-bit. Whatever this bit is in 11-bit. Once you are encounter this a call, then first whatever the program counter, the address of the program holds, that is 16-bit, it is stored into the stack pointer. And as well all the flags of your program, it stored in stack. And then whatever your program counter, it is added with your 11-bit address and jumps to a particular location and executed your instruction. Once is executed, at the end we return the RET instruction. I will discuss later how this will be executed. Similarly, we have the long call instruction. That long call, in the sense the address specified in your the call instruction, it is 16-bit. Similarly, it is works when the program counter encounter this L call, your program counter address is stored into the stack as well as all the flags, it is stored in the flags, and your program counter is added with the 16-bit of an address and jumps to the particular location. Once executed your program, that is what you written in the subroutine, it comes back to the main program by the instruction RET instruction, return instruction. So return, it works as simple as jump instruction to the main program where you called from. It is a difference in jumps to the return instruction. So once it is encountered by your program counter, whatever you stored in the stack, like your the main program address, that is a program counter address, and whatever your flags, that is all restored back to your flag register, and the program counter, it is restored into your program counter. That means that where you call the program, like if you have an a call, let's say an address of whatever the bit, and this is your address whatever it return address, your program counter has jumps to here and executed the next instruction. This is how the process is happening. So that is what I called as a subroutine. In the main program, I call the a call. This is the label, what I mentioned. This holds an address, as in 13-bit as well as a 16-bit address. Your program counter has jumps to the label where it is specified and executed the program, that is the subroutine program. And whenever you return is encounter, it return back to your main program and executed here the sequence of this. This is how the program execution of your subroutine is working out. So let me take one simple example how we use the subroutine program repeatedly, because if I the same program, if I am written so many times, that will take length of the program is more. So here I am simple example, I am written that okay, let it be. Here example I am taking as in just a blinking of an LED. I connected one LED to your port 1.0 bit. So initially the port 1 all become F, that is meant by it is 1. Initially all the ports become 1. So then it is a reverse biased so that your LED will be off. So because once your VCC has connected to this, that should be blink. Okay. So once you made this LED blink, so first what I am written is clear that bit, that means LED will be off position. You making this as 0. Then you call some amount of delay here when it is coming here, executed the program. That much of time your LED will be off position. That we need to calculate according to the mission cycle has taken to execute the instructions what to written in delay program. Once it is a written RET instruction, it is come back to here. Then the bit you made it as 1 here, that is LED will be on now. Port 1.0 bit will be 1. Then LED will be on. Then again you call the delay here, executed. That many time, let's say 1 millisecond or 10 millisecond, that time until that your LED will be on. So this is continuation takes place when LED will be off, or within that there is a delay time. Okay, so how we can calculate the delay? Here the concept is the call instruction. The same program I can write it here, the same program I can write it here instead of calling this program, subroutine program. Now you think on that, how the length of the program is more and program understanding is very difficult within the same line. If you written as a subroutine program, then it is very easy. We can call so many times as well. The length of the program is reduced and the execution of the program is increased. Okay, now we'll see that concept of mission cycle. See, one mission cycle, it means that one instruction, that is 1 byte of instruction, one instruction takes how much time to complete the process. That is we called as one machine cycle. So let me see that probably we know 8051 has an inbuilt oscillator. It is a 12-bit, 12 oscillations has generated itself. That is what we call as a 12 oscillations. Okay, so that is always time is 1 by 12. That is what we call as a time period of one clock cycle. It is 1 by 12 microsecond. If you have the 1 t states, that means one time it takes 2 clock cycles. If you 2 clock cycles, that is what we call as a 2 machine cycle. Okay, that will be multiplied with 1 by 12 into 2. That much of your total time taken to execute 1 t states. Let's say if we have the machine cycle for our crystal frequency, it is 11.0592 megahertz and 16 megahertz. As I told that 8051 has a 12 oscillations. So if you have the frequency, crystal frequency is 11.0592 megahertz, so that divided by 12, it is given the total frequency is 921 kilohertz. That is total machine cycle. So that into conversion to T, that is 1 by F, that is equal to 1.085 microsecond for your crystal frequency is 11.0592. As similarly, if you have the 16 megahertz, so we have the 12 oscillations divided by 16 megahertz, that much of microseconds of machine cycle will take to execute your one instruction. Okay, let me take one simple delay program to take the how much machine cycle for that. See, for example, I have the instruction like I'm making as in A as AA in the sense it is 100. I can rotate or complement, that bit will be, or each bit will be complemented. So port 0 I am making as A, moving that value into that, whatever the accumulator content, that is AA. I am calling the delay 1 here, the complementing that A, that will be continuous loop. So here the delay, how much time it is taken to your port 0 become complemented. So let me have the total length of the instruction or machine cycle. Move instruction will take 1, DJNZ will take 2, RET instruction will take as 2 cycles. So that here you can see that move instruction R0 is FF, that is in decimal it is 255. FF is 255. Sorry, my pen has a problem here. So that 1 plus this takes the next we have the 2 total mission cycle. This DJ and Z will works with the R0 value. R0 has FF, that is 255, that much of 2 cycle, plus RET instruction is 2. Totally it is 513 mission cycle. So 513 mission cycle into whatever your time, whatever your into that clock frequency, that is a time, that will be a total time taken. Similarly, if you have the R0 is FF, R7 is FF, okay. Now the first inner loop, that is R7, I am doing that is 255. That what happening here is 1 plus 2 into 255, okay. So that whatever 1 plus 255 plus whatever your 2, your R6, that is an outer loop, that totally it is rotated until your FF, that is 255, and plus 2 it is for RET instruction. So that will be taken as a total mission cycle. I think you got the concept how we can calculate the total mission cycle for a program. Let me have some simple program with respect to this, how much clock cycle will take for this. So this is the program whatever we written. So instead of I taken as a port 0, I am making 0. So then I move this port 0.1 to hash 00 H. Next I am using complementing the bit port 0 dot 0 I am using instead of 1 because I verifying it is simple. Then I am call the delay. Okay, so here just I am using jump instruction to back 1. So back 1 I supposed to use it here where we getting complemented. 1 second. This is the program. So what is happening here? Just I am port 0 I am making as a complemented, that is 0 1 0 and I am doing. So the next the concept is I am calling the delay program what I am written here. So as we discussed here, the delay is taken as FF no. I'll take the only 2 period here instead of 3 period. So that I will get how much delay we can calculate here. So I am deleting any one of this delay. Move R to FF and move R0 FF. So DJ and Z R0 back here, DJ and Z R2. Here I am using back 3. Okay, DJ and Z back 3, and this I am deleting. So what I'm doing here is same program I'm taken here to calculating my delay FFFF. So instead of the same thing, I am using the same program. Okay, so let me have the total 1308 13,000 sorry 1,30,818 machine cycle will take for this. So that for that our frequency calculation, let me see how much it will be. Let me save this program, and before that I'll keep that to my crystal frequency. It is 12 megahertz. So 1 microsecond that will be taken. Yes, I'm just what I'm doing is port 1 I'm making as 0 and complementing that port 1. Okay, here bit 0. I'm complementing the bit 0. Call the delay, so that whatever that port 1 become 0 and 1 0 with this amount of delay. Let me have the execution. So in the line number 10 we have an R2 or not R2, back 2 it is there, so that should be not mentioned, sorry, back 3 it is. Okay, let me run this program. Okay, so once I debug this, we'll see that in that we'll go with the peripheral. I'm taken the port 1, so let me take the port 1 here, right? Let me run with the step-by-step execution. Now port 1 becomes 0 0, all becomes 0. Now I'm complementing that port's bit 0, that is 0 become 1 now, as well as I'm calling the delay. It comes to here, it takes execution of some amount of time and it return back. I'm written that out of step out steps. So likewise now become 1, it become 0. Likewise it is 1 0 1 0, it is running. So you can see that it will be 1 and 0 1 and 0. Now I want to see that the time how much it is taken with this delay, so that you go to the peripheral, analyze, go to the logic analyzer. So go to setup, because I'm taken as a port 1 here, so delete this port 2, take one, it is a port 1 I'm taken. Okay, so that port 1, it should be the display type should be bitwise, make it as key. So here let me make it as clear waveform. So you can see that it is 1 0 1 0 it is taken. So when the port 1.0 become 0 and it is taken some amount of delay and come back and become 1, so that I want to see that. See, for example, when the port 1.0 become 1, the period is this time. When it comes to 0, it takes the time delay of how much it will be is 0.1345 seconds. That much of time it is taken. Okay, so this is the time has delay has calculated. You can observe that total time delay, it is how much it is taken. If you want to signal information, you can see that delta variation, most position and reference point position. With respect to that, you're getting as 0.13525 time has taken for on period as well as half period. I am created as 50% of duty cycle. So likewise I can calculate the delay for making as port 1 or any port. You can make it as 0 or 1. So This is what we just explaining the concept here. Thank you very much.